Section 9 of National Geographic Magazine, Volume 2, Numbers 1 and 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Rivers of Northern New Jersey by William Morris Davis. Part 2. Look now at the drainage of the crescentic Watchung Mountains, the curved edges of two great warped lava flows of the Triassic belt. The noteworthy feature of this district is that the small streams in the southern part of the crescent rise on the back slope of the inner mountain, and cut gaps in both mountains in order to reach the outer part of the central plain. If these streams were descended directly, or by revival from ancestors, antecedent to or consequent upon the monoclinal tilting of the Triassic formation, they could not possibly, in the long time and deep denudation that the region has endured, have down to the present time maintained courses so little adjusted to the structure of their basins. In so long a time as has elapsed since the tilting of the Triassic formation, the divides would have taken their places on the crest of the trap ridges and not behind the crest on the back slope. They cannot be subsequent streams, for such could not have pushed their sources headwards through a hard trap ridge. Subsequent streams are developed in accordance with structural details, not in violation of them. Their courses must have been taken not long ago, else they must surely have lost their heads back of the second mountain. Some piratical subsequent branch of a larger transverse stream, like the Passaic, would have beheaded them. The only method now known by which these several doubly transverse streams could have been established in the not too distant past is by superimposition from the Cretaceous cover that was laid upon the old Schooley peneplain. It has already been stated that when the highlands and this region together had been nearly base-leveled, the coastal portion of the resulting peneplain was submerged and buried by an unconformable cover of waste derived from the non-submerged portion. Hence, when the whole area was lifted to something like its present height, a new system of consequent streams was born on the revealed sea bottom. Since then, time enough may have passed to allow the streams to sink their channels through the unconformable cover and strip it off, and thus superimpose themselves on the Triassic rocks below. We should therefore find them, insofar as they have not yet been readjusted, following inconsequent discordant courses on the under formation. The existing overlap of the Cretaceous beds on the still buried Triassic portion of the old Schooley peneplain makes it evident that such an origin for the Watchung streams is possible, but it has not yet been independently proved that the Cretaceous cover ever reached so far inland as to cross the Watchung ridges. Want of other explanation for the Watchung streams is not satisfactory evidence in favor of the explanation here suggested. There should be external evidence that the Triassic area has actually been submerged and buried after it was base-leveled to the Schooley peneplain and before it was uplifted to its present altitude. Other streams as well as the ones thus far indicated should bear signs of superimposition, and if adjustment of the superimposed courses has begun, it should be systematically carried farthest near the largest streams. I shall not here state more than in brief form the sufficient evidence that can be quoted in favor of the first and second requisites. Suffice it to say that the overlap of the Cretaceous beds, which contain practically no Triassic fragments, on the beveled Triassic strata at Amboy and elsewhere, indicates submergence after baseleveling, and that the pebbles, sands, and marls of the Cretaceous series point clearly to the highlands as their source. The submergence must therefore have reached inland across the Triassic formation at least to the margin of the crystalline rocks. Some shoreline cutting must have been done at the margin of the highlands during Cretaceous time, but the generally rolling surface of the old peneplain leads me to ascribe its origin chiefly to subaerial wasting. Moreover, the north branch of the Raritan between Mendham and Peapack, Figure 1, and the Lockatong, L, a small branch of the Delaware on the West Hunterdon Sandstone Plateau, gives striking indications of superimposition in the discordance of their courses with the weaker structural lines of their basins, so unlike the thoroughly adjusted course of the Musconetcong and its fellows, the Powhatcong, the Lopatcong, and others. The third requisite of the proof of the inland extension of the Cretaceous and the resulting superimposed origin of the Watchung streams may be stated in detail, as being more in the line of this essay. Has the adjustment that accompanies superimposition systematically advanced farther near the large streams than near the small ones? The character of this adjustment should be first examined deductively. Given a series of streams of different volumes flowing southeastward in the direction of the present dip of the remnant of the Cretaceous cover over the former inland extension of this superposed formation, how will these streams react on one another when they sink their channels into the underlying Triassic formation? The conditions during the formation of the cover of Cretaceous beds are illustrated in Figure 2, where the Triassic portion of the peneplain is submerged, and the shoreline of the transgressing ocean has reached the margin of the crystalline rocks. The waste from the crystallines is spread out as a series of gravels, sands, and marls on the base-leveled Triassic area. Then follows the elevation and tilting of the peneplain with the cover on its back, and with this regression of the sea, there is an equivalent gain of new land. A smooth, gently sloping plain is revealed as the shoreline retreats. Streams run out across it from the crystalline area, or begin on its open surface, growing mouthward as the land rises. 3 such streams, A, C, D, are shown in Figure 3. Their opportunity for deep valley cutting is indicated by the depth of the new base level, BL, below the general surface of the country. While these streams are deepening their channels in the Cretaceous cover, which is unshaded with marginal contour lines in the figures, their subsequent autogenetic branches are irregularly disposed, because there is no lateral variation of structure to guide them. But after a time, the base-level surface of the buried Triassic beds is reached, as is shown by linear shading in the valley bottoms of figures 4, 5, 6, 7. The growth of the subsequent branches then developed will be along the strike of the Triassic softer beds, that is, about square to the course of the 3 transverse streams under consideration. The most rapid growth will be found on the branches of the largest stream, A, because it will most quickly cut down its channel close to the base level of the Tyme, and thus provide steep sloping valley sides, from which the subsequent branches cut backwards most energetically. In due time the main streams discover the particularly resistant transverse lava sheets in the underlying formation, and then the subsequent branches of the largest transverse stream on the upstream side of the obstructions, for example, F and G, figure 4, will have a great advantage over those of the smaller streams. The most rapidly growing subsequent branch, G, figure 5, of the largest transverse master stream, A, may grow headwards so fast as to push away the divide, X, which separates it from the head of the opposing subsequent branch, J, of the next adjacent smaller transverse stream, C, and thus finally to capture and divert the headwaters, H, of the smaller transverse stream to the larger one, as in figure 6. The divide creeps while the 2 opposing subsequent branches are in contest. It leaps when the successful subsequent branch reaches the channel of the conquered stream. The first stream captured in this way must necessarily be the nearest to the large stream. The diversion of the considerable volume of headwaters, H, to the channel of the small subsequent branch, G, causes it to deepen its channel rapidly. The same effect is perceptible in H for a distance above its point of capture and diversion. The increased load of sediment thus given to G will be in great part dropped in a fan delta where it enters the flat valley of the master stream, A, figure 6. Gaining strength by conquest, other captures are made, faster for a time, but with decreasing slowness, as the head of the diverting subsequent branch recedes from the original master, and at last equilibrium may be gained when the headwater slope of the diverting branch is no greater than that of the opposing subsequent branch of the next uncaptured transverse stream. After the capture of a transverse stream has been effected in this way, the divide, Y, between its diverted upper portions, H, figure 6, and its beheaded lower portion, C, will be pushed downstream by the growth of an inverted stream, V. This goes on until equilibrium is attained and further shifting is prevented on reaching the hard transverse lava sheets, Z, figure 7. Here the divide is maturely established. In the case of a system of transverse streams, C, D, etc., figure 7, successively captured by the subsequent branch of a single master, the divides Z, Y prime between the inverted V, V prime and beheaded C, D portions of the captured streams will for a time present different stages of approach to establishment. The divide on the line of that one of the original streams C that is nearest to the master stream A may reach a final stable position Z, while on the next stream further away from the master, the beheaded portion D may still retain a short piece above the gap in the upper lava sheet not yet secured by the inverted stream V', and a third stream further away still from the master, not shown in Figure 7, might remain uncaptured and independent. It is by such tests as these that we may hope to recognize the occurrence of partial adjustment in the streams of the Watchung Crescent as a result of their superimposition on the Triassic formation from its former Cretaceous cover. The greater the degree of complexity in the tests proposed, the more confidence we shall have in the theory when the tests successfully meet the facts. Hence the reason for deductively carrying out the theoretical conditions to their extremest consequences, in order to increase the complexity of the tests that are to be confronted with the facts. This, as a matter of method, seems to me of great practical importance in any attempt to decipher the past progress of geographical development. The admirable contoured topographic maps of New Jersey, issued by the Geological Survey of that state under the leadership of the late Professor George H. Cook, afforded means of applying the deductive tests above outlined without the necessity of plodding over all the country concerned. But however good the maps are, it is hardly necessary to say that they can be interpreted with a better appreciation of the facts that they represent after an excursion on the ground has given the student some personal acquaintance with it. This I have tried to gain on various occasions, maps in hand. Atlas sheet number 6, including the central red sandstone area, and the 5 mile to an inch geological map of the state, present in the clearest manner the facts of form and structure involved in our problem, and to my mind the correspondence between theory and fact is very striking. The Pequannock Passaic is the master transverse stream of the region. Its preeminence was probably due in the beginning to its gathering, from the unsubmerged highlands, a greater amount of drainage than belonged to any other stream that ran southeastward down the gentle slope of the newly revealed Cretaceous cover. It was at that time a compound composite river, compound because it drained areas of different ages, composite because these areas were of different structures. Existing examples of compound composite rivers are seen in the Catawba, the Yadkin Pedee, the Cape Fear, and the Neuse rivers of North Carolina, which all rise on the inland crystalline area and traverse the coastal quaternary plain before reaching the sea. But unlike these, there must have been, when the old submerged land rose with the Cretaceous cover on its back, numerous small streams whose drainage area lay entirely within the Cretaceous plain. These were simple streams flowing over a structure of one kind and one age. Their modern homologues are seen in the Maurice, the Great and Little Egg Harbor, and the wading rivers of southern New Jersey, and I suppose also in various relatively short streams of North Carolina, such as the Lumber, Great Cohera, and Moccasin. It cannot be supposed that the original Pequannock Passaic possessed the large southern branch, which I shall call the Upper Passaic, by which Great Swamp is now drained. Footnote: It should be recognized that the present roundabout drainage of the Great Swamp is a post-glacial feature, determined by the morainic barrier that crosses the basin from Summit S to Morristown M. The pre-glacial drainage of the southern part of the inner crescent was undoubtedly of a simpler and more direct pattern. End footnote. For had this been the case, the divides between the branches of the Upper Passaic and the heads of the small streams that now still cross both of the trap ridges must have long ago been driven to a stable position on the crest line of the inner ridge. The Upper Passaic member of the Pequannock Passaic system must be regarded as a branch of subsequent development, guided by some of the softer Triassic beds when they were reached beneath the Cretaceous cover, and very successful in capturing and diverting other transverse streams that were smaller than its master. For some distance on either side from the Pequannock Passaic gap in the trap ridges at Patterson, the existing streams are perfectly adjusted to the Triassic structure. That is, the ridges are persistent divides, and the lateral subsequent branches of the master flow along the strike of the softer shales and sandstones, except where lately thrown off their courses by glacial drift barriers. This I interpret as meaning that the Pequannock Passaic master stream hereabouts made so early a capture of adjacent superimposed streams that all traces of their initial discordant courses have been obliterated by the development of structurally accordant subsequent streams. The Watchung ridges extend only about 8 miles northward of the Patterson gaps, but reach 30 miles southwestward. It is therefore chiefly in the latter direction that we may expect to find examples of incomplete adjustment following superimposition and capture. At Millburn there is a deep gap in First Mountain, and opposite this at Summit S, Figure 1, a partly drift-filled gap in Second Mountain. This I am disposed to regard as the former outlet of the Rockaway-Rahway River, which on account of its considerable size was not captured by the Passaic until it had cut its passage across the trap sheets almost to a safe depth. The diverted upper portion, the Rockaway, now joins the Passaic, its crooked course from the highlands via Boonton, BN, being a post-glacial irregularity. The beheaded lower portion, the Rahway, heads on the ridge of Second Mountain, retains the pair of subsequent streams between the two ridges, and flows in diminished volume to the sea, the divide between the two portions being in its mature, stable position on Second Mountain. South of the Millburn Gap, there are 3 streams that maintain water gaps in First Mountain, and 5 head branches of these 3 streams rise behind the crest of Second Mountain. These must be interpreted as remnants of streams that once rose further inland, and whose upper courses have been captured by the victorious Upper Passaic. But it is noteworthy that here, at the greatest distance from the gap of the master stream at Patterson, the divides between the diverted and beheaded portions of these southern streams should lie in unstable positions back of the crest line of Second Mountain. This is exactly what the hypothesis of a superimposed origin for these streams would require, and if the complexity of accordance between deduction and fact here presented be duly considered, I believe new confidence may be gained in the hypothesis of superimposition already rendered likely from other evidence. The rectangular courses of the streams that cross First and Second Mountains southwest of Milburn do not militate against their initial obliquely superimposed courses, for, as Gilbert has shown, oblique courses across tilted beds, alternately hard and soft, will gradually shift until they follow rectangular courses along the strike of the soft beds, and square across the strike of the hard beds. Middlebrook, at the southern bend of First Mountain, near Bound Brook, B.B., presents the peculiarity of branching east and west while on the trap sheet of the mountain. This may be due to a retention here, where the dip is moderate, of an initially superimposed bifurcation, or to guidance by fractures at this point where the course of the mountain changes rather abruptly. The facts at hand do not serve to make choice between these alternatives. End of section 9.